Hi, welcome to the CILVR Seminar Series. Today we are very excited to have Nandan Kumar Jha, who will be speaking on entropy and private language models. Nandan Kumar Jha is a fifth-year PhD student at the NYU Center for Cyber Security, advised by Brandon Legal. His research lies at the intersection of deep learning and applied cryptography. He has developed several architectures which were published in ICML, Neurons, CMLR, including an ICML spotlight paper. Please join me in welcoming Nandan. The stage is
And thank you, Radhika, for the introduction. Hi, everyone. Today, I'm going to present our work on cryptographically secure, privacy-preserving machine learning. So first, I'm going to start with the private inferences. So given the two-party settings where in a client and server settings, client has the raw input and the server has the trained model. So raw input can be your medical data, your finance data, which are privacy sensitive. So as a user encrypts their input and sends the encrypted input to the service provider. And service providers performs computation on encrypted data without decrypting it and sends the encrypted prediction back to the user. And finally, user decrypts the prediction. In this way, service provider doesn't know about what's inside the input, and this preserve the client's privacy and protects the server's model, because the model is not on client side, it's on service provider side. So going back to the brief history of the private inference, how it has started. So it has started from a seminal work from 2009, Craig Gentry, FHE using ideal lattice. And first time in 2009, they showed that it's possible to do the fully homomorphic encryption. And they showed that it's possible to do mathematically, but there was no any software developed by that time. And in 2016, Microsoft Research published their work CryptoNets in ICML, and they showed that you can do the MNIST type of image encrypted prediction. So it was a high latency at that time. And further in 2018, the GELU is from MIT, and they did on CIFAR-10 and MNIST. And in 2020, this Delphi work from UC Berkeley, they did on CIFAR 100, CIFAR 10. And the first time they introduced the notion of online and offline computation. In offline, when the user's input are not available, you can do the heavy computation. And online, once the input is available, you can do the all the nonlinear computation. And in 2021, we published our work in ICML 20. So in this work, we found that the neural networks has lots of, redundant nonlinear computations, such as ReLU in the initial stage of the network. So you can remove those nonlinearity without sacrificing the accuracy. And in this work, we outperformed the Delphi by 3.5x runtime at ISO accuracy. And in 2022, there is another work from NYU CCS. It's selective linearization. And in 2023, there is another work at iClear. It's called secure networks. And in 2024, we have another work, deeply safe, where we showed that there is no online, offline things. The end-to-end runtime matters, and we optimize the network not for nonlinear. We optimize the networks for nonlinear as well as linear computation, means the flops. Yeah, if you have any question, you can ask in between the talk.
So this work done on MNIST, or is it done?
Oh, so till this point, deep reshape, It's done on CIFAR 100 and Tiny ImageNet. So Tiny ImageNet image size is 64 cross 64. And there is no work on LLM private inference till this point. Yeah, so from Delphi onwards, 2020 onwards, each work used the hybrid protocol, homomorphic encryption for matrix multiplication, and MPC for all the nonlinear computation. So Delphi used Garble circuit computation, and in DeepReduce, we use the same Garble circuit. But nowadays, people use oblivious transfer for nonlinear computation.
But you're not including this. Like people are using a bunch of this.
Yes, yes. Oh, yeah, yeah. MPC former. Yeah, it was on this entire work is on CNN. There is no work. We haven't included here the transformer models. Yeah. So in transformer, there was I think NeurIPS 2022, Iron, and then MPC former. Yes. So coming back to the private inference on language model, it has very high latency. If you see, even for GPT-2, a small model which has 125 million parameters, and the context size 128. For one single token prediction, it takes 8.2 minutes and 25.3 gigabytes of communication. And this is for two-party computation. Like the threat model is, there is only two-party, and there is no extra parties to have additional assumption, security assumption. And I think MPC former has three-party computation.
So just, this is no encryption, no nothing.
No. This is, everything is encrypted.
Oh, this is.
Yeah. Yes. Yeah. Because the plain text inference is usually in like millisecond. So this is where everything is encrypted. So 128 prompt length or context size is encrypted using homomorphic encryption and MPC techniques. And there are, so this we have done on our own server. We have two remote servers in the lab. And you can see if you scale the context size to even half K, 512, one single token takes half an hour. And 145 gigabytes of communication between two parties is required. So if you look at what is the main source of inefficiency, this is the latency and communication breakdown from paper Cypher GPT, secure two-party GPT inference. So you can see all the nonlinear computation, GELU, LayerNorm, Softmax, they constitute more than 50% in both latency as well as communication. MATML is the linear computation, which is flops. Trunc is the truncation, because when you do the computation, perform computation in field arithmetic, you need to do the truncation. So the motivation for this is to design the LLMs with fewer nonlinearity, so that you can have the faster encrypted computation. So in today's talk, I'm going to cover these topics, like how understand the role of nonlinearity in LLM. And for that, we use the Shannon entropy as a quantifiable metric. And we successively remove the nonlinearity and see how the LLM's training stability and information flow impacted by those removal. And further, we remove the feed-forward nonlinearity, and we have only softmax nonlinearity. So we call it as softmax-only architecture. And in softmax architecture, we have inference-efficient alternative for normalization layer. And we design the entropy-guided attention to have better performance in the absence of crucial nonlinearities. And Another technique that we use is entropy regularization. So these all techniques are to make the inference faster, reducing the number of nonlinear computation at inference time, and stabilize. And in the absence of training, we stabilize the training. And finally, we will discuss about one recent work which talks about how you measure the information flow through the feed-forward network nonlinearity, how you analyze the latent space dynamics in feed-forward. Why we need the entropy dynamics of LLM? So entropy tells you about how the information flows through each attention head and each layer. And it also tells about the critical failure mode in the LLM, such as entropy collapse. So entropy collapse implies the training instability in LLMs. It's from ICML 2023 work. So this is attention score. This one is, yeah. This is the attention matrix where Aij is your attention score. And since it's a softmax probability is greater than equal to 0, and sum over context length is 1. So Aij is the softmax score corresponding to the ith query and jth key. And for that, we compute the entropy, which measure this attention score spread. So this is over one. This entropy is for one attention head, which simply do the arithmetic mean over the length, context length, because we have one entropy values for one softmax, and in one query we have, let's say, 128 or 256 softmax operation. So to compute the entropy of one attention head, we just average the softmax over all the query length. So higher entropy implies exploratory attention, and lower entropy implies the focused attention. So higher entropy means that particular attention head is in exploration mode, and attention score is distributed over multiple tokens. And lower entropy means attention score is it's more like one hot input vector. So we see how the entropy dynamics in the baseline models. So this is the first one is baseline model with GELU nonlinearity. It is GPT-2 train model, a GPT-2 model, 12 layers and 12 attention head in each layer. And 768 is the model dimension. And the second one is the baseline model with ReLU activation. So you can see that all the layers starts with the higher entropy state, and throughout the training, each layers either go into exploration and some goes into exploitation, and most of the attention heads in the layers remains in the having the between the max and mean entropy values. And this is the final snapshot of the once the network is trained. And if you look at how many attention heads are having max entropy values or minimum entropy values. So we have divided into 4 bins, 0 to max by 4, and max by 4 to max by 2. So you can see almost 85 to 90% of attention heads have the entropy values in the max 4 to 3 max by 4, means there is very few attention head having the extreme entropy values. Extreme means either too low or too high. So the yellow one shows the entropy values of particular attention is very high, and the blue one shows these attention heads are in exploitation mode, and these attention are in exploration mode. And in between, other entropy of other attention heads are like the half of their max values. So what happens when you, let's say first we remove the LayerNorm and see how this entropic behavior of attention heads change. So first we start with the normalization-free language model. So in normalization-free language model, we see an opposite trends. Normalization-free model with GELU nonlinearity underperform with compared to the ReLU nonlinearity. So if you can see, this is the baseline model, the first two, and these two are the normalization-free model, and you can see the eval perplexity of normalization-free with ReLU activation is lower throughout the different context length, and there is a significant gap. And this work we have presented in NeurIPS workshop, and we look into why this happens, like when you use GELU nonlinearity in normalization-free, why it's underperformed. So this is the entropy dynamics when you have GELU and ReLU nonlinearity in normalization-free model. So one thing you can see is when you have GELU nonlinearity, the attention heads in the early layers has very high entropy states compared to when you have ReLU nonlinearity. So this is more similar to the baseline model. If you see the percentage of attention heads that has very high entropy state is like the almost 60% of attention heads lies in the last bin. So that means most of the attention heads is still in the exploration mode. You can see here in high entropy state, and this is somehow there is underutilization of the multi-head attention diversity. I mean, each head, there should be very few attention head that should be in exploration mode, but almost more than 50% attention heads are in exploration mode. So, yeah. Yeah. I mean, we train it for one epoch. So, I mean, we can see this behavior from the beginning of like just from like 10K steps. This is a consistent behavior. It may be the case if you train, let's say 10 epoch or so, maybe, or if you use the different training recipe, then maybe GELU will converge. So this is the same training setup as baseline. There is no any different initialization.
Converge faster.
Yeah.
Which means that it may not converge where it may converge at a later step.
Yeah. So
as if you want to get this entropy graph at the convergence of the final model, right? Because you want to get with the final model.
no, if you use LayerNorm, you'll pay the additional cost of nonlinear computation at inference time. So no, so once the model is trained, yeah.
It doesn't cost so much because you're doing it in practice, right?
Yeah, but when you do without LayerNorm, you're saying? Yeah. So yeah, we haven't seen like if you train for like say 10 epoch or so, what will be the behavior? Yeah. So we see how these in the absence of LayerNorm, how the feed-forward nonlinearities stabilize the network. And the ReLU is of course much more faster when you use encrypted inference compared to the GELU. It is just a comparison. ReLU is like significantly faster than GELU in all the encrypted computation.
Another concept.
No, but in GELU, it's much more complex. You need multiple rounds of communication. Yeah.
So I'm confused. You're saying it's faster, but it takes more communication, which will make it slower. Right?
No, GELU takes much more runtime and much more communication. Yeah, we have the final latency breakdown at the end, like how when you replace GELU, how faster it becomes the end-to-end runtime, and how the communication overhead reduces. So in ReLU has only one comparison operation, and in GELU people usually approximate using polynomial approximation or some other method, and you need many more comparison and many more polynomial evaluation. Yeah. So yeah, so this is just for one epoch, and if you keep training, we'll set an epoch. We don't know whether GELU will converge or not. So this is a favorable condition for encrypted inference because ReLU is faster than GELU, and you can see the ReLU has better performance in normalization free model. So to further test it, whether it's what's the natural preference of normalization free model. So we have the learnable slope for each layer in the in ReLU we have fixed like the zero slope for negative. So we make the learnable slope for each layer in somewhat like leaky ReLU format and see how the learnable slope converge over time. So we can see that the learnable slope already by default converges to the zero-like behavior in both the configuration. Here we have only one learnable slope for entire network, where we have 12 slopes, one for each layer. And we can see that throughout the training, all the slope by default naturally converge to the zero in slope. So this further emphasize that the ReLU-like behavior for in the normalization free model. And if you see the entropy dynamics, this is quite similar to the ReLU nonlinearity. So even if you have smaller negative slopes, such as 5e minus 2, you can see the entropy collapse just after like 12 steps. So till this point, it's fine. And after that, you can see the entropy values goes to the near to the zero, which signifies there is entropy collapse. And this you can see the value of nans appearing in the deeper layer of the network. And both happens exactly at the same time. So even if you have even if you have like 0.005 negative slope, training won't converge. Any questions? Yeah, now we study the behavior of LayerNorm and GELU free models. Like we further remove the feed forward. There is no non-linearity in feed forward, and we call this model as a softmax only model. So first we see that their training behavior. So we can see the degenerated attention patterns, like early layers stuck in high entropy. Early layer attention head is stuck in high entropy state and deeper layer in low entropy state. And this implies the training instability, and this implies the entropy overload, and which leads to the underutilization of multi-head attention. So the problem is you can't even train a softmax only model. So we look at how can we stabilize the training without incurring the cost of LayerNorm at inference time. So there are T techniques that we use. One is weight normalization and another is a spectral normalization. These normalization techniques are used in GANs to stabilize the training. And the benefit of this normalization technique compared to the LayerNorm is these normalization techniques applied on the weights, not on activation. So you do all the nonlinear computation at training, and at inference, it's just a simple scalar multiplication. So we see that if you apply the weight normalization or a spectral normalization, or even you simply have the learnable scaling in the feed-forward network, it can stabilize the training of Softmax only model. So the lower one showing the entropy collapse, and the upper one is showing that it finally recovers when you apply these normalization techniques. And in terms of performance, the third one, scaled feed-forward networks, perform better than the first two methods. So we finally use the scaled feed-forward configuration in the Softmax only model. So we solve one problem, which is training instability. And now another problem is the higher entropy state in the early attention heads. So to mitigate those, we use learnable temperature for each softmax operation. So now the attention matrix becomes a function of temperature T, and entropy also becomes a function of temperature T. So when the temperature is greater than 1, there is diffusion in attention score, and when the temperature is less than 1, there is attention score becomes more peaked. So you have something learnable attention, and we, on top of this, we apply the entropy regularization such that the temperature will learn during the training, such that it doesn't stuck in the higher entropy state. And we presented this work in AAA workshop. So coming back to, why we need the entropy regularization, even we have the learnable temperature in the attention matrix. So the thing is, training the softmax temperature is quite difficult. I mean, in particular, we found that if you initialize those temperature with 1, it never works. So we initialize with 1e minus 2, and there are other careful initialization techniques in the entropy regularization, and and there are two key feature in the entropy regularization scheme. One is we compute the deviation from a reference point, and then we penalize during the training. So penalty is compute only if the deviation is deviation cross some threshold margin. It means that we allow some of the deviation in the network. It means we penalize only if the deviation cross a particular non-zero values. And we see that when you have learnable threshold for each attention head, so each attention head learns different threshold during the training, and you can see the non-zero variance, and mean is also different for each layer. So by having the learnable threshold for each attention head in the Softmax model, you somehow preserve the attention head diversity, which is not there in the absence of GELU and LayerNorm. And the second one, why we need the tolerance margin, is when you have the zero tolerance margin, and when you keep increasing the tolerance margin, you can see the spread of the entropy of each layer. It keeps spreading. So it means by controlling this tolerance margin, you can allow some of the attention heads to have higher entropy values, which is a natural property of a well-behaved attention distribution. In particular, if you see how this prevent the over-regularization, like, so if you have zero, if you keep increasing the tolerance margin, the population of attention heads with higher entropies keep increasing, and you can, it gives you finer level control to like where you want to stop. Yeah.
It's not harm. It should be attention. That's like an optimization harm, right? It's not related to.
Yeah,
severe
so there are very few attention heads that needs to be in higher entropy state. There are very few, like.
You're acknowledging that to get it better.
Yeah. So if you constrain, like if you penalize even the slight deviation from your threshold, it's like it's killing your, it's like kind of over-regularization. Naturally, there should be some attention head which should be in high attention, high entropy state. So through this tolerance margin, you have done one knob, you can control this behavior.
This model, right? You're getting rid of LayerNorm, which would be very difficult for secure inference, but it's a rescaling that it's not means that training, and you're replacing that rescaling with.
Yeah, like parametric normalization means you're replacing with any techniques which do the nonlinear computation only at training time, but not at. Yeah,
it's just a scale.
Yeah, yes. These regularization will force the networks to learn such that your entropy dynamics in is a well-behaved region. Like it penalizes when the model deviates from well-behaved dynamics. So, this is the final model. When this is the baseline model, which has all the non-linearity, LayerNorm, Softmax, and GELU. And first, we remove all the non-linear LayerNorm and feed-forward non-linearity, and we merge both the linear layer into one, because effectively now we have two consecutive linear layers, so effectively you can merge them in one. And in next step, you make the softmax learnable, and you use the entropy regularization as to force those attention heads to be in well-behaved region. So you can see these normalization techniques prevent the entropy collapse. There are very few attention heads with very low entropy values, but it doesn't prevent the entropic overload. So once you apply the entropy regularization, it finally prevents the entropic overload. So there are very few attention heads that are now in extreme region. So yeah, coming to the experimental results. So we compare with this work, simplifying transformer blocks, which design the normalization free model without losing any performance. So we apply our softmax techniques, softmax only techniques in their model, and we compare with our model. So their perplexity is worse compared to the like our techniques. And yeah, if you can see the communication and latency savings, you can achieve like 4x communications and 1.9x latency saving. But definitely this is there is, compared to the baseline model, this performance is still worse. And that you can see in this, we train on three different number of training tokens, 1.2, 2.4, and 4.8 billion tokens. So you can see this our softmax only models is much more worse compared to the baseline model because we remove much more non-linearity. But compared to any state-of-the-art techniques, this works better. And yeah, this is the latency and communication saving breakdown. So if you simply replace GELU with ReLU in the baseline network, you can get 35% of latency reduction, end-to-end runtime, and 2.7x communication reduction. And when you remove the LayerNorm, you again get better, you keep getting better and better savings. And finally, when you do some flop optimization, your communication is almost same, but your runtime, you'll get better runtime. So the setup for this is we use exact same configuration to AMD server with 256 gigabytes of RAM, and in the through the Linux command, Linux traffic command, we set this 100 megabytes of communication bandwidth, 30 milliseconds of link latency, and number of threads on each machine is 32. And we evaluate using this Bumblebee framework, which is like NDSS 2025 paper. And yeah, I mean, this is actual end-to-end latency. There is no approximation. So the model code is in JAX, and we install the Docker, their Docker version, and we run on both the machine.
You compare against them because they're
No, we are not comparing them. We are using their framework to run the end-to-end inference. Yeah, their framework supports the transformer-based language models. So we are using their framework to run our optimization and how it performs, like how it saves runtime and communication. We are not comparing against Bumblebee. Bumblebee is a framework to run the LLM inference, and they have their own optimization for GELU and other, like Softmax. For example, for Softmax, they have lookup table. For exponential computation, they use polynomial approximation till, I think.
what is it?
So this is compared to the baseline. Baseline is like with all the nonlinearity, your Softmax, LayerNorm, and GELU. So when you keep removing the nonlinearity, you will get better communication and better runtime. No. We have shown that the perplexity is keep decreasing. Yeah. But when you use let's say entropy regularization, you'll get some better performance, but it is still away from the baseline models. Yeah.
So this is per token?
Yeah, this is for single token for single token generation. So yeah. And this is for context length 128, very small context length. So we cannot even run the 1K context length on both the machines. There is not sufficient RAM. Any question? Okay. So the conclusion from this, all the optimization is like, of course, nonlinearity is like the lifeblood of any neural network, and their removal leads into two critical failure mode: training instability, which is entropy collapse in deeper layers, and entropic overlaid in early layers. And you can mitigate this training instability using either the parametric normalization like weight or spectral normalization, or some other techniques which performs nonlinear computation only at training time. And you need better entropy regularization technique to 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 mimic those attention behavior as well-behaved in well-behaved region. Yeah, this is just one more slide for so till this point we have seen that we can analyze. If you simplify the networks, you remove some component, how it behaves, how the attention behaves. But how, if you have to understand the feed-forward network's behavior, how can you analyze like how the feed-forward non-linearities actually control the information flow in the network? So attention is a probability-based method. So you use Shannon entropy and compute the how the attention score is diffused. But in feed-forward network, there is nothing as like the probability distribution. So this is the work that we submitted in the column. So we use 4 metrics to understand their the latent space dynamics of feed-forward networks. So this is the first one, is the spectral entropy. So we compute the covariance metrics out of their representation, their hidden representation, and then we normalize their eigenvalues. Once you normalize the eigenvalue, it becomes probabilistic distribution. And then you apply the Shannon entropy. And it is also called as, in quantum mechanics, von Neumann entropy, where you have some density operator. And here the density operator is basically your covariance matrix. Another is participation ratio, which is used in neuroscience. So this tells you the effective dimensionality of a latent space. And so the value is, minimum value is 1, and higher values goes to the dimension of your covariance matrix. So for example, if you have GPT-2 model, so the intermediate dimension in feed-forward is 768 multiplied by 4. So maximum participation ratio is your 768 multiplied by 4. Higher means information is distributed across multiple principal component. Lower means there is low utilization of available latent space. And the third one is Jensen's Shannon divergence. Basically, it compares two eigen spectrum. One is like pre-activation, one is the post-activation, and you can see how the eigen spectrum change due to the non-linearity. And basically, you measure the KL divergence over their normalized eigen distribution. And the fourth one is the early eigenvalue early enrichment. Basically, tells how many eigenvalues have the, like how top heavy your eigen spectrum is, like whether just few eigenvalues capture all your variance or it is distributed. And through this, we can understand the normalization behavior better, like why normalization free model with ReLU or learnable works better as compared to the GELU activation. So this is the early eigenvalue enrichment for post activation, and it varies from 0 to 1. 1 means it is top heavy, means there are very few eigenvectors that dominates the eigen spectrum. So this tells you the in GELU activation there are effectively first half of the layer is not doing any effective works, but when you use the ReLU or any learnable slope activation, so the variance is distributed across the eigen spectrum. And these two graphs shows that the feed forward networks in early layers do some like overwork, compensate for the absence of nonlinearity. You can see the dimensionality difference between post-activation and pre-activation is like 250 to 300 times when you use ReLU or learnable sum slope as compared to GELU activation, which goes only like 20 times. So it's like in the absence of LayerNorm, when you have ReLU or learnable slope, the early feed-forward networks try to compensate for those behaviors by spreading the variance across multiple eigenvalues. Yeah, that's it.
Thank you so much, Nana, for the presentation, and thank you all for joining. We have some live discussions here, please, and looking forward to seeing you all in the
Thank you.